Welcome to Papers Simplified, a deep dive brought to you by SILMA AI. And today, we're diving into the Qwen2.5-Omni Technical Report.
From the Qwen team,
Yeah, exactly.
and they introduce a new end-to-end multimodal model called Qwen2.5-Omni.
Wow, so we've got a mouthful today.
Yeah, it's quite a mouthful.
Yeah.
But it's a fascinating piece of research.
Okay, well, give me like the 30,000-foot view. What's so special about this model?
So what makes this model really stand out is its ability to process, like you said, a wide range of inputs, so text, images, audio, video, and simultaneously generate both text and natural speech, all in a streaming manner.
So it's not just receiving these different inputs, it's responding in different ways as well.
Exactly. And that's a really crucial part because think about how we as humans communicate. We don't just use one modality, we integrate them seamlessly. So being able to have a model that can understand different modalities and respond in both written and spoken language in real time is a significant step towards more natural and human-like AI interactions.
Okay, and the research team themselves, they highlight this challenge.
Yeah, so they emphasize that, efficiently unifying different understanding modalities and having this dual response capability in text and speech has been a big challenge in the field. And that's what Qwen 2.5 Omni aims to tackle head on.
Okay, well, today we're going to explore how they approach some of these key challenges, like how do you train a model on such diverse types of data? How do you make sure that things like audio and video are synchronized? And then on the output side, how do you make sure that the text and speech don't interfere with each other and enable that real-time processing that you mentioned, especially for that streaming audio?
Yeah, all great questions, and we're going to delve into each of those aspects.
All right, let's start with the heart of it. Tell me about the architecture of this model. What makes it tick?
At the core of it is what they call the thinker-talker architecture.
Okay, the thinker-talker architecture. That sounds kind of interesting. Tell me about how it's split up. What does the thinker do, and what does the talker do?
So think of the thinker as the brain of the operation.
Okay.
It's responsible for processing all those incoming inputs, whether it's text or audio or video, and generating those high-level representations and the text output.
So it's doing all that heavy lifting of understanding the input.
Exactly. It's really trying to understand like the meaning behind those inputs, what they represent at a higher level, and then translate that understanding into text.
Okay, and it actually generates the text output as well.
Yes, so the thinker generates the text, and then the talker comes in to handle the speech aspect. So think of the talker as the voice, if you will. It takes those high-level representations and the text from the thinker and uses that to generate the speech tokens in a streaming fashion.
Oh, okay, so this is where we're getting to that real-time feel.
Exactly. And the talker itself is described as a dual-track autoregressive transformer decoder.
Dual track, what does that mean in this context?
So dual-track essentially means that it's handling two parallel streams of information and generating those streams autoregressively. Likely one for the audio tokens themselves, and another for some sort of context or control information that guides the speech generation.
Okay, so it's not just spitting out words, it's also making sure they sound natural and flow together properly.
Precisely. And the key here is that the talker doesn't just receive the final text from the thinker. It actually gets access to those rich, high-level representations directly and shares its own historical context back.
So it's a much more interconnected system than just having separate modules for text and speech.
Yeah, and that's a crucial aspect of their design. By having that close connection, they create a cohesive single model that can be trained and used end-to-end. This way, the speech generation is not just tacked on at the end, it's very tightly integrated with the understanding part, which is key for achieving a natural and coherent flow between what's being understood and how it's expressed vocally.
Okay, that makes sense. So we have this thinker-talker architecture, and we know they're working very closely together. But now let's zoom in a bit. How does the model actually handle these different types of inputs, like text, audio, images, and video? How are they processed?
So each of these inputs has to be converted into a form that the model can work with, what we call hidden representations. These are essentially numerical summaries of the input data that capture its core features and meaning.
Okay, so it's turning all these different types of data into a common language that the model can understand.
Exactly. For text, they're using Qwen's own byte-level byte pair encoding, which is a way to efficiently represent textual information using a large vocabulary of tokens.
And what about audio? How do they convert audio into these numerical representations?
So for any audio input, whether it's standalone audio or the audio track of a video, they first resample it to a standard 16 kilohertz. Then they transform it into a 128-channel MEL spectrogram.
Okay, a Mel spectrogram. Break that down for me a little bit. What is that?
So a MEL spectrogram is a way of representing the frequency content of audio over time.
Okay, so it's like a visual representation of the sound waves.
Exactly. And they're using the audio encoder from their previous model, Qwen2 Audio, to process this MEL spectrogram. Each frame in this representation corresponds to roughly 40 milliseconds of the original audio.
Okay, so it's like taking snapshots of the audio signal every 40 milliseconds.
Exactly. And then for visual inputs, for images and videos without sound, they utilize the vision encoder from their Qwen2.5-VL model. This is a vision transformer architecture, which is very powerful for processing visual information.
So it's essentially treating images and videos as sequences of visual tokens that it can understand, similar to how it handles text as sequences of words.
Yes, exactly. And for video, they do something interesting. They sample the frames dynamically to match that 40 millisecond audio sampling rate we talked about earlier. And for still images, they treat each image as two identical consecutive frames.
Oh, that's interesting. So they're basically trying to maintain that 40 millisecond timescale even for static images.
Exactly. And it's likely done to ensure consistency in how the model processes different types of visual inputs. But then they also have this novel approach to handling positional information, which they call time-aligned multimodal rope, or TM rope.
TM rope E, that sounds pretty important. So tell me about it. What's its purpose?
So ROPE stands for rotary position embedding. It's a technique commonly used in transformer models to tell the model where each element is located within the input sequence. TMRP is their extension of this concept to handle three-dimensional positional information: temporal position, height, and width.
Okay, so it's not just about the order of words in a sentence, it's also about where things are in space and time.
Right. So for text and standalone audio, they use identical position IDs for the height and width dimensions, so essentially like a one-dimensional ROPE for text. But audio also gets an absolute temporal position encoding.
So each 40 millisecond chunk of audio gets its own unique timestamp.
Yeah, and that makes sense because the order of sounds over time is crucial for understanding audio. But when you move to images, the temporal ID becomes constant because it's a static image. But each token, representing a small region of the image, gets distinct height and width IDs based on its location within the image.
So it knows not only what it's looking at, but also where that object or feature is located within the image.
Exactly. And then for videos with audio, things get even more interesting. The audio is encoded as usual with its temporal IDs, but for the video, they treat it as a sequence of images. Each frame gets an incrementing temporal ID, and those IDs are dynamically adjusted based on the actual frame rate of the video.
Dynamically adjusted. Why is that necessary?
Well, different videos can have different frame rates,
Right.
so they need to make sure that those temporal IDs are always aligned with that 40 millisecond timescale we've been talking about.
That makes sense. So they're basically stretching or compressing those temporal IDs to keep everything in sync.
Exactly. And by doing that, they ensure that the model can accurately relate the audio and visual information in terms of their timing, even if the video frame rate is not constant. And then when you have multiple modalities combined, like text and an image, the positional numbering for each modality just continues from where the previous one left off.
Okay, so it's like creating one big continuous stream of information with consistent positional encoding across all the different input types.
Precisely. And to handle video with audio simultaneously, they use this interesting technique called time interleaving.
Okay, time interleaving. What's that all about?
So they segment both the audio and video representations into these 2-second chunks.
Okay.
And within each chunk, they place the visual information first, followed immediately by the corresponding audio information.
So they're interleaving the visual and auditory information in these 2-second blocks.
Exactly. And that helps the model to learn those fine-grained temporal relationships between what's being seen and heard. It's like presenting the information in a way that highlights those close connections in time.
Okay, that makes a lot of sense. So we've covered how the model takes in all these different types of data. Now let's talk about how it generates responses. The paper mentions that the thinker uses pretty standard techniques for generating text.
Yeah, for text generation, the thinker utilizes common autoregressive sampling techniques.
Okay. Remind me what autoregressive sampling is.
So essentially, it predicts the next word in the sequence based on the context of the words that have come before it.
Okay.
And they can use additional methods like repetition penalties and top sampling to make sure the generated text is more diverse and interesting.
Okay, so that part's pretty straightforward. But the speech generation, that seems much more complex, especially when you consider the need for it to be streaming and sound natural.
It is definitely more involved. The talker receives two important pieces of information from the thinker.
Okay.
One are those high-level representations of the input. These essentially capture the meaning and the context of what's being said.
Okay.
But it also receives the embeddings of the actual text tokens that the thinker generated.
Okay, so it's getting both the meaning and the specific words.
Yes, and both are crucial for generating natural-sounding speech.
But why both?
Well, because of that streaming aspect, the speech generation has to start even before the entire text has been finalized. So the high-level representations give the talker an early indication of the overall tone and attitude of what will be said.
Okay, so it can start generating speech with the right emotion and emphasis from the beginning?
Exactly. And then the text tokens come in to provide the precise phonetic information, making sure the words are pronounced correctly. Because the high-level representations, they focus more on semantic similarity, which means that words with similar meanings might have close representations, even if they sound very different.
So it needs those specific words to disambiguate any potential pronunciation issues?
Right. It needs to know exactly which word to say, not just what the general idea is.
Hmm.
And then to make the speech generation efficient for streaming, they've developed a specialized speech codec called Qwen2.5 tokenizer.
Qwen2.5 tokenizer. Okay. What does a speech codec do?
So a speech codec is essentially a way to compress and represent speech information digitally.
Okay.
And this particular codec is designed to compactly represent the essential information needed for speech. And it can be decoded into that continuous speech stream in a causal manner.
Causal meaning it processes the speech sequentially, like we humans do.
Exactly. And interestingly, the report emphasizes that the speech generation doesn't require strict word-level or even timestamp-level alignment with the text.
Oh, that's interesting. So the speech doesn't have to be perfectly synchronized with the text in terms of timing?
Right. The talker doesn't have to predict the exact moment when each word should be spoken. This simplifies the process and allows the model to start generating audio tokens and text tokens concurrently in a more natural and flexible way.
Okay, that makes sense. So the talker has a little bit more freedom to generate speech that flows naturally without being constrained by rigid timing requirements.
Exactly. And that's important because human speech is not perfectly timed. There are pauses, hesitations, changes in pace. So by giving the model that flexibility, they can make the generated speech sound much more human-like.
Now, a major focus in the report is on the designs for streaming, particularly on how they minimize the initial delay before you hear the first audio.
Yeah, that initial latency is crucial for a good streaming experience.
Yep,
If you have to wait too long before you hear the first sound, it breaks the flow of the conversation.
absolutely. And they mention this concept of support pre-filling in that context. What is pre-filling and how does it help reduce that initial delay?
So pre-filling is essentially a technique where you start processing some of the input even before the full input is available.
Okay.
And to support this in a multimodal setting, they modified both the audio and visual encoders to be more efficient.
Okay, so they can start processing chunks of audio or video without waiting for the entire file to be loaded.
Exactly. For audio, instead of attending to the entire audio input at once, the encoder now performs attention in these 2-second blocks.
Okay, so it can start processing those blocks as soon as they're available.
And the vision encoder uses something called flash attention, which is a more efficient way to process attention in transformers.
Okay, so both the audio and visual encoders are optimized to start working on smaller chunks of data, reducing that initial waiting time.
Precisely. And then on the output side, for generating the audio waveform, they have this streaming codec generation technique, which is also designed to minimize latency.
Okay, tell me about that.
So for long audio sequences, they use a sliding window block attention mechanism within a flow-matching DIT model.
A sliding window.
Yeah, so it's like a window that moves along the audio sequence. And the model only pays attention to the information within that window.
Okay, so it's only looking at a limited amount of past context at any given time.
Exactly. They group adjacent audio codes into these blocks, and the DIT's attention is limited to a small number of these blocks, a few in the past and one in the future. And this allows the model to generate the MEL spectrum, which is that intermediate representation of the audio, in chunks. And each chunk has the necessary context from its neighboring blocks.
So it's like building the audio output piece by piece, ensuring each piece has the information it needs from its immediate surroundings?
Right. And they also use this chunk-by-chunk approach with a modified version of Big VJAN, which is a model for generating waveforms from MEL spectrograms.
Okay.
So both the MEL spectrum generation and the waveform generation are optimized for streaming.
So it's all about breaking things down into smaller, manageable units that can be processed and generated quickly, which is essential for that real-time feel.
Exactly.
Okay, so we've got this amazing architecture, we've got these clever techniques for streaming. Now let's talk about how they train this whole thing. The report describes a three-stage pre-training process, and it sounds like it was pretty extensive.
It was a very involved process designed to give the model a really strong foundation across all these different
All
modalities.
right.
So the first stage, they actually kept the parameters of the large language model, which is the core text processing part, frozen. They focused on training the vision and audio encoders using a massive data set of audio text and image text pairs.
So they're essentially teaching the vision and audio parts how to understand and relate to the language that the LLM already knew.
Yeah, that was the main goal. They wanted those non-textual encoders to develop a semantic understanding that was aligned with the LLM's knowledge. And then in the second stage, they unfroze all the parameters so the LLM, the vision encoder, and the audio encoder were all trained together. And they used a much broader range of data. This included a lot of image and video data, video data with audio, all sorts of multimodal data.
So this is where the model really starts to learn those intricate connections between all these different types of information.
Exactly. They wanted the model to be able to integrate information from different sources and understand those complex relationships. And then the third stage focused specifically on long sequences. They trained the model on data with a sequence length of 32,000 tokens.
Wow, that's a lot of tokens.
Yeah, it is. And this is important because longer sequences are more challenging for the model to handle. They require a deeper understanding of context and long-range dependencies.
So they were basically pushing the model to its limits in terms of how much information it could process and remember.
Exactly. And the goal was to make sure that the model could handle things like long videos, extended audio conversations, and documents with both text and visual elements.
Okay, so that makes sense. And they also did something interesting with the training data. They replaced those hierarchical tags with natural language prompts. What was the purpose behind that?
So this was based on some of their previous work with Qwen2 audio. They found that using natural language prompts instead of more structured tags led to better generalization and instruction following across different modalities.
Okay, so it's more like how humans naturally communicate. We don't use those structured tags when we talk or write.
Right, it's a more natural way to give instructions and provide context to the model. And in terms of initializing the different components of the model, they leveraged existing high-performing models.
Okay, so they didn't start from scratch, they built on a solid foundation.
Exactly. The LLM was initialized from Qwen2.5, the vision encoder from Qwen2.5-VL, and the audio encoder from Whisper Large V3, which is a very powerful audio recognition model.
So they took the best of what was already out there and used that as a starting point.
And they trained adapters on the encoders first before fully training them, which helps to stabilize the initial training process.
Okay, so it's like a gradual warm-up process before they hit the heavy lifting.
And after the pre-training, there's a post-training phase where they fine-tuned the model for specific tasks and further improved its abilities.
Okay, tell me about that.
For the thinker, the text generation part, they used instruction-following data formatted in ChatML. And this dataset included pure text dialogues, conversations involving images, audio, and multimodal combinations. They wanted to make sure the model could understand and respond appropriately to all sorts of instructions that involve different types of data.
So they were really trying to teach it how to be a versatile and adaptable conversational AI.
And for the talker, the speech generation part, they had their own three-stage training process.
Okay, tell me about that. What were the stages?
The first stage focused on context continuation, making sure the generated speech flows naturally within a longer conversation.
Okay.
And then the second stage used a technique called direct preference optimization, or DPO, to improve the stability of the speech generation.
Okay, and what does that involve?
So essentially, they trained the model to distinguish between examples of good and less desirable speech generation, and to learn from those preferences to generate more natural and consistent speech.
Oh, that's clever. So they're essentially using feedback to guide the model towards better performance.
Right. And then the third stage was multi-speaker instruction fine-tuning to make the generated speech sound even more natural and to give them more control over the speaker's voice.
Okay, so they wanted to be able to specify things like the gender, the accent, or even the emotion of the speaker.
Exactly. And they also used in-context learning, or ICL, to further improve the talker's abilities.
Okay, remind me what in-context learning is.
So in-context learning is basically the ability of a model to learn from examples that are given to it within the current conversation without needing to be explicitly retrained.
Oh, okay, so it can adapt on the fly.
Right. And they trained the talker on a speech continuation task using dialogues with those multimodal contexts and spoken responses, which helped it learn that intricate mapping between semantic understanding and how it's expressed in speech.
Okay, so it's learning how to take the meaning of something and turn it into natural-sounding speech, taking into account all those subtle nuances of pronunciation, prosody, and even emotion.
Precisely. And they used a technique called timbre disentanglement to ensure that the model doesn't associate specific voice characteristics with certain text patterns that might occur less frequently.
Okay, that makes sense. So they're trying to avoid any biases or inconsistencies in the speech generation.
And then to really fine-tune the speech generation and make sure it was as stable and natural as possible, they actually used reinforcement learning.
Reinforcement learning. That's usually associated with training agents to perform tasks in an environment. How did they use it for speech generation?
So they created a data set of good and less desirable speech outputs for the same input. And they use reward scores based on things like word error rate and punctuation pause error rate to guide the model towards generating more accurate and natural sounding speech.
Oh, that's interesting. So they were essentially training the model to maximize its reward by producing speech that sounded as close to human speech as possible.
Exactly. And to round it all off, they did speaker fine-tuning, which allowed them to fine-tune the model on data from specific speakers, so it could learn to mimic their voice characteristics and style.
Okay, so you could have the model respond in the voice of a particular person if you wanted.
Precisely. And that can be very useful for personalization and creating more engaging interactions.
Okay, so it sounds like they really threw everything but the kitchen sink at this model in terms of training techniques and data. How did they actually evaluate all of this? How did they know if it was working?
So they evaluate the model in two main areas. Its understanding capabilities, meaning its ability to take in different types of inputs and generate text-based responses, and its speech generation capabilities.
Okay, so let's start with the understanding part. How did it perform on text-to-text tasks, which are kind of the bread and butter of language models?
So on those standard text-based benchmarks, Qwen2.5-Omni's performance was generally comparable to their previous models, Qwen2.7b and Qwen2.5-7b, sometimes a little better, sometimes a little worse, depending on the specific task.
Okay, so it's at least on par with those very strong language models in terms of its core text processing abilities.
Right. And then for audio to text, where the input is audio and the output is text, it performed really well.
Mhm.
It was either better than or comparable to state-of-the-art models on tasks like automatic speech recognition, speech-to-text translation, speaker emotion recognition, all sorts of audio understanding tasks.
Okay, so it can really understand what's being said in audio and translate that into text accurately.
Exactly, and it did particularly well on audio reasoning tasks, where it had to not only understand the words, but also infer meaning and draw conclusions from the audio input.
So it's not just transcribing, it's actually understanding the content of the audio at a deeper level.
Right, and it also performed very strongly on voice chatting benchmarks, where it had to understand and respond to spoken prompts in a conversational setting.
Okay, that's impressive. And what about image understanding? How well did it perform on image-to-text tasks?
So for image understanding, it performed comparably to their dedicated vision language model, Qwen 2.5 VL7B, and it surpassed other open source omnimotor models on those benchmarks.
Okay, so it's at least as good as specialized vision language models, even though it's designed to handle all sorts of modalities.
Right, and it actually outperformed a smaller version of GPT-4o on many of those benchmarks.
Wow, that's impressive. And it sounds like it has strong visual grounding capabilities, meaning it can accurately identify and locate objects within an image.
Yeah, so it can not only understand what's in the image, but also where things are located within the image. And for video understanding, specifically videos without any accompanying audio, it also excelled. It outperformed other open source omnimodal models and GPT-4o Mini on those benchmarks.
Okay, so it seems to have a good grasp of understanding the content of both static images and dynamic videos.
Yeah, and it's really interesting because it seems to be able to leverage its understanding of those different modalities to improve its performance on the other modalities. So by understanding audio and video, it can improve its text processing and vice versa.
So they're all complementing each other in a way.
And then when you look at its performance on multimodality tasks, where the input is a combination of different modalities, that's where it really shines. It achieved state-of-the-art performance on a benchmark called OmniBench, which is specifically designed to test understanding of those mixed inputs.
So it's not just good at handling individual modalities, it's really excelling at integrating and understanding information from different sources.
Exactly. And as a testament to the success of their approach, of having this unified model that processes all these different types of data in a cohesive way. Now let's move on to the speech generation evaluation. They tested it on zero-shot speech generation, which means generating speech from text without any specific training for a particular voice or style, and on single-speaker speech generation, where it was fine-tuned to mimic the voice of a specific person.
Okay, and how did it perform on those tests?
So in the zero-shot setting, it showed very competitive performance in terms of content consistency and speaker similarity compared to other leading text-to-speech systems.
Mm.
And importantly, those reinforcement learning techniques they used really paid off here, making the generated speech much more stable and natural sounding.
Okay, so even without any specific training for a particular voice, it can generate speech that is both accurate and pleasant to listen to.
Exactly. And then when they fine-tuned it for a single speaker, he was able to capture their prosodic style really well and achieve near human levels of quality, according to both subjective human evaluations and objective metrics.
Okay, so it can really learn to sound like a specific person, which can be incredibly useful for a lot of different applications.
And they also highlighted that the fact that its performance on voice instruction following is now comparable to its performance with text input is a significant step towards more natural and intuitive voice-based interactions.
So the gap between how well it understands spoken instructions and written instructions is getting smaller.
Exactly.
Right.
And that's crucial because voice is becoming an increasingly important way for humans to interact with technology.
Right. We have voice assistants, we have smart speakers, and we're seeing more and more devices that can be controlled with our voice. So having a model that can understand and respond to spoken instructions as effectively as it can with text is a big deal.
Exactly. And it points towards a future where our interactions with technology are more natural, more intuitive, and more accessible to a wider range of people. And they do acknowledge that there are still areas for improvement, particularly in things like video OCR, which is optical character recognition from video, and audio-video collaborative understanding, where the model needs to really understand those connections between what's being seen and heard.
So there's still room for growth, but this seems like a really impressive step forward in terms of multimodal AI. Before we wrap up, maybe we could summarize some of the key takeaways and the novel aspects that were presented in this paper.
Yeah, so one of the big takeaways is the introduction of that thinker-talker architecture, which enables simultaneous text and streaming speech generation by separating those processes but maintaining that tight integration between them.
And that time-aligned multimodal rope, TM rope, that was a pretty clever way to handle the synchronization of audio and video, wasn't it?
Definitely. It's a really innovative way to make sure those temporal relationships are captured accurately. And then on the efficiency side, using blockwise processing in the encoders so that pre-filling is possible, that was crucial for achieving those low latencies for streaming.
And using that sliding window attention in the flow matching DIT model, that helped a lot with generating the audio output quickly and efficiently as well.
Absolutely. And then overall, their approach to pre-training and post-training with those 3 stages of pre-training and the targeted fine-tuning for both the thinker and the talker really demonstrates a very thoughtful and well-designed process.
And it definitely paid off because they were able to achieve some really impressive benchmark results.
So overall, Qwen2.5-Omni seems to be a very strong step towards a more unified and versatile multimodal AI.
It really does seem like a glimpse into the future of human-computer interaction, doesn't it?
It does. Yeah, and it's exciting to think about all the possibilities that this kind of technology can unlock, whether it's in areas like communication, accessibility, or just making our everyday interactions with technology more natural and enjoyable.
Yeah, and it'll be interesting to see how this field continues to evolve. Who knows what kinds of amazing multimodal AI systems we'll have in the next few years.
I'm really looking forward to seeing what the future holds.
Me too. Well, on that note, I think we'll wrap things up here.
Yeah, thanks for having me.
Thanks for joining us.
It was a pleasure to be here.
And as always, thanks to all of you for listening.
We hope you enjoyed this deep dive.
Until next time.